In algebra, variables and constants usually represent real numbers. The values of trigonometric functions are also real numbers. Therefore, the language and operations of algebra also apply to trigonometry. Algebraic expressions involve the operations of addition, subtraction, multiplication, division, and exponentiation. These operations are used to form trigonometric expressions. Each expression on this slide is a trigonometric expression. A statement of equality between two expressions that is true for all values of the variables for which the expressions are defined is called an identity. For example, this expression is an algebraic identity. An identity involving trigonometric expressions is called a trig identity. If you can show that a specific value of the variable in an equation makes the equation false, then you have produced a counterexample. It only takes one counterexample to prove that an equation is not an identity. For example, prove that sine of x multiplied by cosine of x is equal to tangent of x is not a trigonometric identity by producing a counterexample. Suppose x is equal to pi over 4, and then replace each x in the trig functions listed with pi over 4. The sine and cosine of pi over 4 will be equal to the square root of 2 over 2. Meanwhile, the tangent of pi over 4 will be equal to 1. If you multiply square root of 2 over 2 by itself, it will result in 1/2, which is not equal to 1. So solving this equation shows that the equation is not an identity. Although producing a counterexample can show that an equation is not an identity, proving that an equation is one generally takes more work. Proving that an equation is an identity requires showing that the equality holds true for all values of the variable where each expression is defined. Several fundamental trig identities can be verified using geometry. You may remember from previous lessons in your class that functions can be defined using the unit circle. From the unit circle, the sine of theta is equal to y over 1, or y, and cosecant theta is equal to 1 over y. That is the sine of theta equal to 1 over cosecant of theta. Identities derived in this manner are sometimes called reciprocal identities. Notice how each reciprocal identity can be reversed. You can solve for a cosecant if you are given the sign. A quotient identity is defined as a function that is equal to two values or two trig functions divided against each other, resulting in the answer as a quotient. So tangent and cotangent are both quotient identities, as tangent of theta is equal to sine of theta over cosine of theta, and cotangent of theta is equal to cosine of theta over sine of theta. So Pythagorean identities are based upon Pythagorean theorem, a squared plus b squared is equal to c squared. And there's one primary Pythagorean identity upon which others are based, and that is sine squared theta plus cosine squared theta is equal to 1. And you can see we have two others that are derived from that. You have 1 plus tan squared of theta is equal to secant squared of theta, and cotangent squared of theta plus 1 is equal to cosecant squared of theta. And looking at the example at the top of this slide, you can see how that's derived. You take the primary theorem and you divide it by cosine squared theta all across the board. And that results in every identity within the equation changing. You have sine squared theta over cosine squared theta becoming tangent squared theta, and then you have the two cosine squared thetas simplifying to 1, and 1 over cosine squared theta reducing to secant squared theta. And conversely, you can get the other identity, that of cotangent squared theta plus 1 is equal to cosecant squared of theta. You get that by dividing the original theorem by sine squared theta all across the board. And you can try that yourself and see if it works out. So here we have an easy example of a reciprocal function. We have secant of theta is equal to 3 over 2, and we are told to find the cosine. Now, if we remember from the previous slide, cosine of theta is equal to 1 over secant of theta. And so what that should turn into is 1 over the fraction we were given at the start. And if we have a fraction of a fraction, in this case, you flip the fraction on its head and multiply it against the value on top, the numerator. So that would turn into 1 multiplied by 2 over 3. And anything multiplied by 1 is the same thing. So 2 over 3 multiplied by 1 becomes 2 over 3. So here's another example. It's a bit more complicated though. So we have cosecant of theta equal to 4 over 3, and we're told to find tangent of theta. Now, there are no identities that directly relate cosecant of theta to tangent of theta. The reciprocal functions have a little to no sway here. So we need to go into Pythagorean identities. So here we use cosecant squared of theta is equal to 1 plus cotangent squared theta. And we plug in our 4 over 3 squared, and we evaluate it. That becomes 16 over 9, and you subtract by 1. So 1, in order to subtract it from that fraction, you have to multiply it by the denominator on top and bottom. So that becomes 16 over 9 subtracted by 9 over 9. And that becomes 7 over 9 equal to cotangent squared theta. And then we square root the fraction. And that becomes square root of 7 over 3 plus or minus. And now that we have the cotangent of theta, it's pretty easy to find the tangent. Relating again back to reciprocal functions, tangent of theta is equal to 1 over cotangent of theta. And that is equal to 1 over the square root of 7 over 3. And so the plus or minus is still maintained, but we need to flip the fraction on its head. So that becomes 3 over square root 7. But it's a common mathematical rule, I'm sure you guys know, that you can't have a square root at the bottom. So what do? You multiply square root 7 on both the top and bottom. Square root times the square root canceled, so you end up with 7 on the bottom. And you multiply square root 7 against the top. And so that becomes 3 times square root 7 over 7, or about 1.134 if you're partially using a calculator. So this is our third and final example for this PowerPoint lesson. And this one focuses on some interesting substitution with the Pythagorean identities. We're told to simplify sine of x plus sine of x multiplied by cotangent squared of x. And if you know how to do some basic algebra factoring, the same rule applies here. There is a common factor in sine of x. So you can take that out of the equation and keep it on the outside and have sine of x multiplied by 1 plus cotangent squared of x in the parentheses. Now looking at those Pythagorean identities from the previous slide, you'll see that what's in the parentheses is familiar. 1 plus cotangent squared of x is equal to cosecant squared of x. And so to simplify that, we just substitute that in because they're equal to each other. And so we just put that in. To make it even simpler, we can use reciprocal identities as cosecant is equal to 1 over sine of x. We substitute that in, 1 over sine squared of x multiplied by sine of x. The sine of x goes on top, and 2 of the sines cancel, resulting in a simple 1 over sine of x, which again, with reciprocal identity, simplifies to a single cosecant of x. In review, we learned reciprocal identities, quotient identities, and Pythagorean identities. And we did examples to show how you can solve for each one. Knowing this, you should now have an understanding of how to break down and solve far more complex equations.